Okay, Math 150, we're going to get started on antiderivatives. This is 4.9, depending on the book you're using, but basically this is the beginning of the last exam, the material that will be covered in the last exam. So we're going to work with antiderivatives, and they mean exactly what they sound like. They are the undoing of a derivative. So something that you really want to kind of embrace is if you know how to do derivatives, then you should know how to find antiderivatives, okay? And here's kind of the thinking behind it. So if we find f prime of x right here, so f of x equals x cubed, so then we know, you know what, let me write this in green. So we know that f of x prime would be 3x squared. We know for g of x prime would be 3x squared. And we know h of x prime would be 3x squared. So you notice that each of these functions are different functions. X cubed plus 7, and x cubed minus pi are three completely different functions. Now they're related by the parent function, but they are still different functions. And it turns out their derivatives were all identical. So this can cause a problem when working with the antiderivative. So we're going to have to account for that. Okay. Now, here's the thing. What the antiderivative does is it says what would happen if you undid that, okay, what the derivative did. And that's not the only thing. There's more to it than that, but that's just kind of the beginning idea behind it. So here's a more precise definition of the antiderivative, what it actually is. So it says f of x is an antiderivative of f of x on an interval, a closed interval a to b, if big capital F prime of x equals f of x for all x in element of AB. The most general antiderivative of a function f of x is f of x, big F of x plus c, where c is an arbitrary constant, okay? So I have a little note right here. This is something important. Knowing your derivatives will help with antiderivatives, okay? So it's kind of like when you know your times tables, it makes you better at division, even though you didn't learn like division tables, but by knowing your times tables, it's the opposite operation. So think of antiderivatives and derivatives as opposite operations, okay? For me personally, I've always thought, now this is not mathematically correct, but this is just something that makes sense to me, how it kind of made it stick, is I always thought of derivatives as kind of tearing things down. And that's really only when you're dealing with polynomials and stuff, because when you're dealing with sine functions and exponentials and stuff, it doesn't actually tear them down. They just stay the same or alternate. But what helped me think about it is the derivative, I feel like it destroys, it tears things down. And the antiderivative is trying to put them back together. Okay, now that's, again, that's not mathematically correct, but that just helped me kind of think about it. So maybe that'll help you guys. And just like with many things, it's very easy to destroy something and tear it down, and it's much harder to put it back together. So antiderivatives do require a little bit of finesse sometimes, a little bit of creativity. They're not always as brute force as derivatives can be. So we're going to learn kind of the basics of antiderivatives and the fundamental theorem of calculus in chapter 5 as well. So let's go down here and let's take a look at, let's use our knowledge of derivatives to find the most general form of the antiderivative of the following. So let's say that we have f of x is equal to 6x plus 2. So now we're going to go back up to the definition and kind of see what it's saying. It says big F of x is an antiderivative of lowercase f of x on a to b if the derivative of big F is actually f of x, okay? So that means whatever we say the antiderivative is, so let's call it big F of x. Whatever we say this is, that means that when we differentiate it, when we take the derivative of it, we should get back to the original f of x that we started with, okay? So this is a way you can check yourself, kind of like with factoring. You know, you could factor something and then you could FOIL it out to see if you did it right. Similar thinking. If you say that this is the antiderivative, I can just check real quick if you're right besides knowing how to do it, by just taking the derivative of whatever you just said you found. And if the derivative of what you say is the antiderivative is not the original f of x, well, then you didn't find the antiderivative. And so you can always check yourself. But what does that mean? That means you have to be good at derivatives. Similarly, in other types of math like factoring and foiling, if you want to be good at factoring, you probably had to be good at foiling, okay? So it's a similar idea. Again, foiling and factoring is not the same as derivatives and antiderivatives, but the concept behind it is very similar, okay? So then I have to think, what could I write that when I take the derivative of it, I would get 6x? What could I write that when I take the derivative of it, I would get 6x? Well, what if I wrote 3x squared? Right? If I wrote 3x squared, what's the derivative of 3x squared? Boom, it would give me 6x. So that must be it. Now, what could I take the derivative of to get a 2? Oh, 2x, right? Because the derivative of 2x would give me 2. So I'm pretty sure that this is the right antiderivative. But now we run into this little trouble here. Notice how this had a constant, and this didn't have a constant. How do you know which one? How do you know if it's a plus 7 or a plus pi or a minus pi or a plus nothing? How do you know? So we come back here and we just add plus c. So c is an arbitrary constant. You don't know if it's positive, you don't know if it's negative, but you're saying that it is possible, or that there is some constant attached. Now, is it possible the constant is 0? Sure, you can have a constant of 0, no problem. But keep in mind that you've accounted for any possible constant by saying plus c. So now let's find the derivative. Let's find the derivative f prime, like big F prime. So what's the derivative of 3x squared? 6x. What's the derivative of 2x? Plus 2. What's the derivative of c? 0. Boom. This matches the original. We did in fact find the antiderivative. Okay, so that's how it works. So that means knowing your derivatives will help you greatly with your antiderivatives. Let's look at another one. Let's say g of x is equal to 7e to the x. Okay, so we want to find big G. We want to find big G of x, the antiderivative. Well, if you take the derivative of e to the x, what do you get? E to the x. So then the antiderivative will still be 7e to the x plus c. Now, how do I know I'm right? Let's find g prime of x. So this would be 7e to the x plus 0. And once again, we notice that this matches that. Okay? So here's the thing. Right now, finding the antiderivative is just simply about finding the derivative and then working back. So when the problems become more harder, yes, it's still the same concept, but it's harder to look at or harder to see through it. So what you have to do is learn some integration techniques. That'll be what we spend a lot of time on in chapter 5, and then chapter 6 will apply that, okay? So, so far so good. Everybody okay? Hopefully. So let's move on. Okay, so now, hopefully you guys are noticing some rules. So I'm going to give you guys some basic functions. So let's say we have a function, and I'm going to give you some basic antiderivatives. And as it turns out, these will be the same properties that we use for antiderivatives for integration in, I believe it's 5.4. Okay, so 4.9 and 5.4 are identical sections, but in 5.4, they call it integration. Which is the antiderivative, and they're going to use the integration symbol like this. Right now, we're just going to call it the antiderivative, okay? So in reality, these two sections are identical, okay? So then we're going to have antiderivative over here. Okay, I'm not going to write it out. And then let's write out a few functions. So we have a constant k. Let's write out x to the n. Let's write out 1 over x. Let's write out e to the x. These are some of the basic ones, and a to the x, the less common one with a base other than e. I don't use that one as often, but you know, it comes up sometimes. Okay, so what would the antiderivative of any constant be? Well, up here, when we wanted to take, when we wanted to take the antiderivative of this constant 2, right, we just said, well, 2x. So what it is it's k times x plus c. Don't forget the plus c. the plus c, whenever you're doing antiderivatives, you must always account for the constant that the derivative makes 0. You don't know what the constant was, so you always have to attach it. Now, x to the n is written like this: x to the n plus 1 divided by n plus 1 plus c, and n cannot equal -1. Okay, now let's take a minute, think about this. The antiderivative of x to the n. Well, if we were going to say f of x equals x to the n, then f prime of x would equal, take the power, put it in front, rewrite the x, reduce the power by 1, right? So derivatives take exponents, right, that are numbers, and they multiply them, and then they divide, or I'm sorry, they multiply them, and then they subtract 1 from the power. So the antiderivative is the inverse operation of that. So instead of multiplying, we're going to divide, and instead of subtracting 1, we're going to add 1. So that's where this comes from. They added 1 to the power, and then whatever that power is, they divided by it to undo the derivative, okay? 1 over x, well, you guys know that that's the ln of the absolute value of x. Don't forget the absolute value of x, because you'll have to guarantee that x is always positive when you're working with natural logs. This is the case when n equals -1, right? Because this is actually x to the -1. That's why over here they say n cannot be -1, because it's this case right here. Okay. E to the x, well, we know the antiderivative of e to the x is e to the x plus c, because the derivative does nothing, so then the antiderivative does nothing. And then a to the x would be a to the x over the ln of a, right, plus c, because the derivative of that is a to the x times the ln of a. Okay, so we have some basic functions, okay, not a lot, but we're going to learn the trig functions in the next, I think it's in 5.2 or 5.3. Actually, never mind, I think I learned them, we teach them, yeah, we teach them in this one. So we'll go on to the trig functions in a second. Okay, now there is a few properties that we want to use with the antiderivative. So if you remember, the derivative, you could take derivatives term by terms through pluses and minuses, right? You just couldn't do it through products, because then you had to use the product rule. You couldn't just take the derivative product by product. So we're going to say, well, if f prime of x plus or minus g prime of x, well, we could use those rules to undo that with antiderivatives and say, well, then that means f of x plus or minus g of x plus c. So we could find antiderivatives using this format. So we can, you know what, let me write this in red. We can take antiderivatives of sums / differences. We can also take antiderivatives of constants times functions. So that means that if we have some constant k times f prime of x, we can lead to the antiderivative can lead to k times f of x plus c. Where the k kind of just tags along for the ride, you take the antiderivative of the derivative and you get f of x, and the k just kind of tags along, okay? So the main thing with antiderivatives is you really have to keep grounded on the derivative, and you can always check yourself by going back and taking the derivative of whatever you said the antiderivative is, and you better get back to the original function, okay? So find the most general form of the antiderivative, of x equals 1 over 2 cubed roots of x to the 5th plus e to the 7 e to the x. Well, let's say, you know what, let's say 12 e to the x, okay? So we want to find the antiderivative, the general form of the antiderivative. And they say general form because the plus c, right? The plus c could be anything. It's not a particular antiderivative. So it's kind of like you're finding the family of all the antiderivatives associated with this. So it's just another way to talk about that. The plus c kind of takes care of that whole family of them. And then sometimes you'll be given conditions where you can find a particular antiderivative, okay? So the first thing you guys know in general is we have to write f of x as exponents. So 1/2 x to the negative 5/3 plus 12e to the x. Okay. So this is what my f of x is. So then capital F of x, or my antiderivative, will be, now again, with derivatives, we would take the power and put it in front and then reduce the power by 1. But with antiderivatives, what do we do different? We take the power of negative 5/3 and we add 1 to it, right? And then we divide it by negative 5/3 plus 1, whatever that may be, which will end up being what? Negative 2/3. But we'll, and again, you guys can skip steps and everything. I'm just kind of doing this as a teacher for now, and then I'll skip a few steps here and there for speed, okay? Plus 12e to the x. Well, that's just 12e to the x. So remember, I added 1 to the power and then divided by that new power. So let's see what we got here. We have big F of x, let's see, big F of x would be equal to x to the what power? X to the, what is that, negative 2/3 divided by 2, let's see, times, what is negative 5/3 going to be? Plus 1, that's going to be 2/3 negative, okay? So then plus 12e to the x plus c. So let me just clean up my fraction a little bit. I believe we should end up with, oh geez, let me see here, 3/2. So that would be what, 3/4? Negative 3/4 x to the negative 2/3 plus 12e to the x plus c. Yep, that looks good. And that would be your final answer. You don't have to get rid of the negative exponents. I'm totally fine with negative exponents. Again, most of the time you deal with negative exponents and you have to fix them is when you're trying to find critical numbers or there's a reason you're doing it. Okay, so let's look at another example. So we have find big F of x for f of x equals, oh no, let's do this differently. Let's find the most general antiderivative for t cubed plus 7t all divided by the square root of t. Okay, so again, I haven't taught you the quotient rule or the product rule or anything for antiderivatives, so we don't really know how to undo a quotient. So remember, when in doubt, do algebra first. Okay, so I'm going to split this as 2 separate fractions. So this is equal to g prime of t. So this is g prime of t. So then g prime of t is really worth t cubed over the, you know what, I'll write it as a power, t to the 1/2 plus 7t over t to the 1/2. But that's really t to the 3 minus 1/2. That would be what, 5/2? Plus, that would be 7t to the 1/2. So that's our derivative. Okay, so g prime of t, let me write this cleaner. G prime of t is equal to t to the 5/2 plus 7t to the 1/2. Okay, now we haven't actually found the antiderivative. All of this was just to write it in a cleaner form. Now it's in kind of the general power form, right? The x to the n. So now we can find g of t. Okay, we're undoing the derivative, so that just gives us g of t. In this problem, they gave us plain old f of x, so to find the antiderivative of that, that would be capital F of x. So it's just a notation, don't stress too much about that. So we're undoing g prime of t and becoming g of t. That means we're definitely going to still have to use our antiderivative rules, where you do t to the 5 halves plus 1 divided by 5 halves plus 1 plus 7t to the 1 half plus 1 divided by 1 half plus 1. Remember, you divide by whatever power is. Once we start doing more of these, I will just skip right to the answer because you guys can do 5 halves plus 1 in your head. 5 halves plus 1 should be 7 halves. So this will be actually t to the 7 halves divided by 7 halves plus 7t to the 3 halves divided by 3 halves. Notice how this power and this division and this division and this power match. Okay, so then we have g of t is equal to 2/7 t to the 7 halves plus 2/3 t to the 3 halves plus c. And we found our general form of the antiderivative. Okay, so let's take a look at some trig stuff. Okay, now again, if you know your derivatives for trig, then you should have no problems with your antiderivatives. So these are the main functions that we'll work with for trig for now. And in calculus 2, you will add more to your list, and these are the antiderivatives. Okay, so let's do sine of x, cosine of x, secant squared x, cosecant squared x, secant x tan x, cosecant x, cotan x. And then let's do the inverses. So we have 1 minus x squared, and we have 1 over 1 plus x, x squared with no square root, okay? Now, the antiderivative of sine of x cannot be plain old cosine of x plus c. And why not? Well, because if you took the derivative of cosine, wouldn't you get negative sine? And that's not a negative sign on the other side. So what you have to do to adjust is you say the antiderivative is negative cosine of x. Oops, that's pretty. Okay, so then what's the antiderivative of cosine? Well, let's see if it works better this time. Sine x plus c. Now let's double check. What's the derivative of sine x? Cosine x. What's the derivative of c? 0. So it worked perfect. Okay. Secant squared. Now think, what would you take the derivative of to give you secant squared? 10x plus c. You see how that works? That's what you're looking for there. What would you take the antiderivative of? I'm sorry, what would you take the derivative of that would get you back to cosecant squared x? Well, that would be cotan x plus c. However, we got to throw a minus in front because the derivative of cotan is negative cosecant squared. But we need to end up positive, so we throw an extra negative in front. So then the negative and the negative become the positive that we're looking for. And then hopefully you guys know the derivative of what would give you secant x tan x. Well, the derivative of, secant x plus c would give you secant x tan x as your function. So then this one would be negative cosecant x plus c. Okay. Now these two are the ones we use much less in our work, but they do come up from time to time. These are the arc sines. So think, what would you take the derivative of that would get you this guy? Remember, that was one of the special ones, and this was the other special one that I really made you, there's 6 of them, but these are the 2 that I focused on. So this would be sine inverse of x plus c, and this would be tan inverse of x plus c. Now think about it. If I take the derivative of sine inverse, that's the one you memorized, wouldn't you get this guy over here? And if I took the derivative of tan inverse, wouldn't you get this guy over here? So that's how these are the antiderivatives, okay? So now let's practice a few of these. So we come over here and it says the antiderivative for 1 over 5x plus 7 secant squared x plus sine x minus 1 over the square root of 1 minus x squared. Okay, so now let's just kind of use this. So let's call this, let's call this f of x. So then big F of x equals, now remember, maybe I should warn you guys, sometimes they try to throw you off. Remember, this is really just 1/5 x to the negative 1. But if we go over here and we look back up here, x to the negative 1 had an antiderivative of ln of x plus c. So we're going to say, well, this is 1/5 ln of the absolute value of x plus c. And then this one is plus 7 tan x. And then this one, sine of x, is minus cosine of x. And then this one would be minus sine inverse of x. And then plus c. Now, some of you might be saying, now, wait a minute. We did plus c. There should be like 5 plus c's, okay? Or 4 plus c's. Well, you'd be right. But what's a constant plus a constant plus a constant plus another constant? Well, it's just some new constant. So we just say that it's all, when we add them all up, we're going to get some c, okay? So the thing is what I did is I used this rule repeatedly right here. This rule right here says, this rule says that I can take the antiderivative term by term, just like I can take the derivative term by term. This rule says that I can take a constant and hold it off on the side, find the antiderivative, and then put the constant back. So if we scroll down here, we're going to see that f of x equals 1/5 ln of x. How do I know this is right here? How do I know this is right? Think about it. Take the derivative. What's the derivative of ln of x? It's 1 over x. What's 1/5 times 1 over x? Boom, it's 1/5 x, okay? So, so then what's the derivative of 7 tan x? Wouldn't it be 7 secant squared x? Got it again. What's the derivative of negative cosine? It would be positive sine, because a negative and a negative make a positive. And then what's the derivative of arc sine? It's this guy, right? 1 over 1 minus x squared. And then what's the derivative of c? It's 0. And remember, you got a c plus another c plus another c plus another c. Well, that's just some new c. Okay, so don't stress out too much about that. It's just some constant. All right, so let's move on. Let's see here. So we got a little bit left. So this next part says, find f of x given, so I'm going to say find f of x given that f double prime of x equals 2 minus 12x and f of 1 equals 9 and f of 2 equals 12. Okay, so what this is called an initial condition, because they gave us some extra information to help us. Okay, so first we start off with f double prime, 2 minus 12x. Now think about this. How am I going to get back to f of x? Remember, they want to know f of x. So take a minute, think about how you're going to get back to f of x. Again, I've been talking quite a bit right now without pausing. Sorry about that, you guys. Sometimes I get carried away. So I have f double prime, but they don't want f double prime. They want to know f of x, the original function, before it was differentiated. So normally we would start with f of x. We would take the derivative, right? So I'd give you some f of x, right, equals this, and then you'd find f prime of x, and then it equals that, and then we'd find f double prime of x, and then it equals that. But now what I'm asking you to do is I'm asking you to go backwards. I'm asking you to start with the second derivative and work your way up. So let's see how we could do that. Okay. Well, how do you undo a derivative? You use the antiderivative. So then f prime of x would be the antiderivative of 2, which would be 2x, minus 12x squared divided by 2. Do you guys see? I added 1 to the power and then divided by the power. Remember, this was a power of 1. But then I have to add the plus c. Now this would be the first derivative. So how do I get rid of a first derivative? I take the antiderivative of that, and that would give me f of x. But the antiderivative of 2x is going to be 2x squared over 2, right? Because I added 1 to the power and then divided by it, minus, now this is actually what, 6 over 1. So this will be 6x cubed divided by 3 plus c. Now what's the antiderivative of any constant? It's that constant times x. So I have 2x squared antiderivative. I have done the antiderivative of this, and I have done the antiderivative of this. But I just took the antiderivative again, so I need to add another constant. Let's call it d, okay? So the first time I took the antiderivative, I got this plus c. But then I have to have another constant here to count for the next time I did the antiderivative, okay? So now let's look what we have here. So that means that f of x is equal, these cancel, to x squared, these cancel, minus 2x cubed plus cx plus, oops, d. Now here's the thing. They gave us an initial condition. So technically we have not truly found f of x. We just found a family of f of x's, some version of them, right? But we want to know a specific one that has to do with what's up here, these initial conditions. So what I'm going to do is I'm going to find f of 1, and that would be equal to 9, which equals 1, right? Let me plug this in. F of 1 is equal to 1 squared minus 2 times 1 cubed plus c times 1 plus d, and I know this all has to equal 9 because they said so. They told me right here. So then we know that this is actually what? Negative 2 minus 1 would be, or I'm sorry, negative 2 plus 1 would be negative 1 plus c plus d equals 9. So then we know c plus d equals 10 if I just add 1 over, right? Well, they gave us another initial condition because I don't know c and I don't know d yet. So they gave us another initial condition. They said f of 2 equals 12. So I'm going to plug in 2 squared minus 2 times 2 cubed plus c times 2 plus d, and I know this has to equal 12. And again, those of you that are concerned, where am I getting all this from? I'm using my f of x, right? Right over here on the left, I've now found f of x. I just haven't found the specific f of x. So this is what's helping me find the specific f of x. So then we know that this is going to be what? 4, what is that? Minus 16 plus 2c plus d equals 12. Well, that is actually what? 2c plus d equals 24, I believe. Yeah, so now this may look familiar. You now have a system of equations. So now I can write this as c plus d, c plus d equals 10, and 2c plus d, is it 2c plus d equals 24. This is my system of equations. You guys can just take out your calculator. Remember in calculus or in pre-calculus when you learned how to do systems of equations on a matrix? So I'm just going to go into second matrix. I'm going to edit it, and it is a 2-row by 3-column, and it's 1, 1, 10, 2, 1, 24. Okay. So then we're going to go into second matrix again, and we're going to do math, and we're going to find RREF. Oops. We're going to find RREF of second matrix A, and I can write it over here. RREF would end up becoming 1001, 14, negative 4. So I now know C equals 14 and D equals negative 4. If you don't want to use matrices, you can just do the substitution method. I'm just trying to show off that you guys know how to do matrices. So you could just do substitution and solve for C, or you could do elimination and do it just as well. That's just as easy. But now we know C is 14 and D is negative 4. So now we can officially find our true f of x, x squared minus 2x cubed plus 14x minus 4. Okay, so notice these guys, I have now found their actual values. So I have my real f of x. This is my final answer. And I was only able to find a specific f of x because they gave me initial conditions. Okay. Let me just do one more, and then I think I might end the video. So we have, let's do the same thing. Find f of x if f prime of x equals 1 over 3x plus 3 over 1 plus x squared, and f of square root 3 equals 1. Okay, so let's see. We know that we only have to do one antiderivative. So f of x is equal to 1/3 ln of the absolute value of x, right? Because I know that 1 over x, this is really 1 over x, and the antiderivative of 1 over x is ln of x. And if I don't believe it, then I could just take the derivative of this. What would I get? When I get 1/3 times 1 over x, which is that. So then we do plus 3. Now, what's the antiderivative of if this were times 1 over this guy? Wouldn't that be 1 plus x squared in the denominator with a 1 on top? So if we go over here, that's this, right? That's the arctan. So, or tan inverse. So we're going to go over here and we're going to say 3 times tan inverse of x, and then we're going to say plus c. But we know f of 3, square root of 3 is equal to 1, so we're going to do f of square root 3 equals 1/3 ln of square root 3, absolute value, but we know that's going to be fine, plus 3 tan inverse 3. We know that this has to equal 1 because they said so, right? They said the initial condition that it has to be 1 if you plug it in. Okay, so let's see here. I could clean this up a little. I could take the 1/2 power and this would become 1/6 ln of 3, right? Because this is technically 3 to the 1/2. I could move the 1/2 to the front because of properties of logarithms. Let's say plus 3 times, now you have to think what angle would give you the ratio of square root 3 for the tangent. Okay, square root 3 for tangent. I believe that is pi thirds. So we would have pi over 3. You could do your unit circle to figure that out. And then that has to be 1. Oops, where's my plus c? I forgot it right here. Plus c. Sorry about that, you guys. I forgot that. I wrote it above, but not below. So then plus c equals 1. So now, just so you guys know, you're not going to be able to find some nice clean answer. This is 1/6 ln of 3 plus pi plus c equals 1. So then I'm going to say that c equals 1 minus 1/6 ln of 3 minus pi. So I just moved them all to the other side. And in this case, it's negative 2.32469-ish, give or take. Okay, so this one's just one that doesn't clean up, but you found the c. So now we can come over here, and again, this is kind of an approximation, but this is pretty good. We can say that f of x equals, you know what, I'll write it in red. F of x equals 1/3 ln of the absolute value of x plus 3 tan inverse of x plus c. But c is negative 2.32469. And, you know, just imagine I asked you to round off to 4 decimal places or something like that for your c, or 5 decimal places, okay? So this would be our new f of x we discovered, okay, from taking antiderivatives. Okay, you guys, I have a little bit more to do, but I'm running out of steam, so I think I'm going to end the video now. See you in the next class.